Very good morning to all of you. Today we are going to discuss uninformed search techniques, bidirectional search, and also we will compare different uninformed search techniques. First, we can see bidirectional search technique. So, the idea behind bidirectional search is to run two simultaneous searches. So that means one search moves forward from initial state and the other search moves backward from the goal state. So the algorithm terminates when both searches meet in the middle. So that forming a complete path from start node to the goal node. So that means there are two searches. One is from forward to the forward search, that is from initial stage to the uh, goal state it is moving, and backward means it is starting from the goal state and moving to the initial stage. But at a particular point they will meet. So we can say that algorithm stops when both search meets in the middle. So here we can say instead of searching from start to goal in one direction, the search is divided into two small searches. So this reduces the number of nodes explored. So that means it sometimes leads to finding a solution more quickly. We can discuss bidirectional search with an example. In this figure, you can see that here the start node is A and the goal node is L. And we have already discussed bidirectional search that uses two searches. One is backward and another one is forward. These two searches run simultaneously and meet in the middle. So bidirectional search performs forward search from the start node A and backward search will be started from the goal node L. And the algorithm stops when both searches meet at a common point. So we can see initial in the case of forward search, it is starting from A and its child node is E. So it will explore E. Then in the backward search, L has the child node J. So it will explore J. So here in the figure also you can see that from L to J and forward search it is A to E. Then E has two child nodes. So similar to BFS, it will explore all the child nodes. That is here B and G is there. Here you can see from from E it will go B and G. Then in the backward search, J has two child nodes I and M. So it will explore I and M. Here also you can see that. Then Then you can see next level from G has only one child node, that is H, and I has two child nodes H and K in the backward search. So from I it will explore K and H, and from G in the forward search it has two child nodes. One is F and another one is H. Here also you can see. So now we can see both meets at a edge. So this is the common meeting point. So the forward search will be AE, B, G, F, H, and the backward search will be L, J, M, I, K, H. And here the meeting point is the both search meet at node H. So that means here we can write the shortest path to the goal, that is from A to E, then G, then H. And backward search will come from L to J, then I, then H. So we got the path A, E, G, H, I, J, M. That is the upper path. Then we will see. So why this bidirectional search actually is efficient? We can say that instead of searching the entire depth, that is from one side to another, each search explores only up to depth d by 2. And the total nodes exposed are significantly fewer. So we will see. The key motivation of bidirectional search is that here you can see that here d raised to d by 2, that is the search, forward search, and the backward search will be b raised to d by 2, which is much less than b raised to d. Other searches we have seen that it is b raised to d, but here we can see that b is the branching factor and d is the depth, and forward search covers b to the power d by 2 and backward search b to the power d by 2. So then there will be b to the power d by 2 plus b to the power d by 2. So this is expanding two searches of depth d to the b to the power d by 2, and each is much cheaper than expanding one search of the depth d. Then the bidirectional search can be implemented using BFS and also the iterative deepening search. So the algorithm runs two searches, one forward from the start node and one backward from the goal node. And both actually we are using BFS and iterative deepening search. And at least one frontier must be stored in the memory so that the algorithm can efficiently check for intersection between two searches. So here you can see that, for example, if a problem has a solution, D is equal to 6 and each direction run breadth first search one node at a time. Then in the worst case, the two searches meet when they have generated all the nodes at a depth 3. So that will be the worst case. Forward search expand all the nodes up to the depth 3 and backward search expands all the nodes up to the depth 3. Then the two searches meet in the middle. So this drastically reduces the number of nodes generated compared to a single BFS to depth 6. So, and it works only when there is a unique start node and goal node. So that is the application condition there. There is a unique start node and unique goal state. The goal state is explicitly known, and the here a reverse operation or actions that are available for backward search. Then we will see, we have already discussed, that means there is a significant reduction in search time and also suitable for a problem with a large depth, and they have it will be very efficient when the branching factor is high. But there are limitations also. That means it requires extra memory for storing the frontier, and it is not suitable when multiple call state exist. And also, we can say that backward search may not be possible in all problems. So there are the limitations also will be there. And here we will see the properties of a bidirectional search. So bidirectional search is complete if and only if a single goal, otherwise difficult. So that means this is complete. That means a well-defined goal state and reverse actions are available and it is complete. If there are multiple call states, then performing backward search become difficult and completeness is also not guaranteed. Next point is time complexity. So regarding time complexity, when breadth first search is used in both forward and backward direction, the time complexity will be because of d to the power d by 2. So we already discussed the forward search and backward search. It uses BFS. So the time complexity will be d to the power. It will go only up to the depth by 2. That is the worst case up to d by 2. So we are considering b to the power d by 2 where b is the branching factor and d is the depth of the optimal solution. Next, we will see space complexity. Space complexity is also similar to BFS, that is b to the power d by 2. Here, in forward search and backward search, both are happening parallelly, and it will explore half the node. So we can say that it will be b to the power d by 2. So this is because both frontier must be stored in memory for intersection checking. Then coming to the optimality, the bidirectional search can be optimal, but not always. It is optimal only when both searches uses BFS and also all step costs are equal. So we are considering all step costs are equal in the case of BFS. We already discussed. So if forward search and backward search uses BFS, then this is optimal. Then bidirectional search is complete for a single non-goal, and time and space complexity will be of b to the power d by 2, and it is optimal when both forward and backward searches uses BFS with a uniform step cost. Then we will see the comparison of uninformed search strategies. So here we can see we have already discussed all these algorithms. You can see on the first row, breadth first search, uniform cost search, depth first search, depth limited search, iterative deepening search, and a um, bidirectional search. So we discussed all this, and we have also discussed all these properties of all these algorithms. We will just compare all this. We can see we can initially just take we are just taking branching. B is the branching factor, and D is the depth of the shallowest solution, and M is the maximum depth of the search tree, and L is the depth limit, and here we have C star. C star is the cost of the optimal solution. Then here we are considering epsilon also, that is the minimum step cost. Then in the case of breadth first search, here first property we are considering is it complete? Yes. If the branching factor is finite, then it is complete. And time complexity will be b to the power d, and space complexity is b to the power d. And is it optimal? Yes, it is optimal if all step costs are equal. And it explores level by level. Then we are moving to the next one, that is uniform cost search. In the uniform cost search, is it complete? Yes, it is complete. Um, and also time complexity. Time complexity means here in this case, we are considering here we are considering the C star also. C star means cost of the optimal solution. So cost of the optimal solution. So that means b to the power C star divided by epsilon. Epsilon is actually the minimum cost step cost. So C star divided by epsilon plus 1. B to the power C star divided by epsilon plus 1. And here the space complexity is also B to the power C star by epsilon plus 1. And it is optimal, and it expands the lowest cost node first. And then coming to depth first search, is it complete? It is no. It is not complete. Fails in infinite depth spaces. And time complexity will become b to the power m. M means m is also the depth, but m is maximum depth of the search tree. Then there is a difference between breadth first search and depth first search. And here the space complexity is actually b into m, and optimal, it is not optimal. Um, we cannot say that it is optimal. Then very memory efficient, but it is risky. Then depth limited search. Depth limited search, is it complete? No, unless depth limit is above the solution depth, then it is not complete. And the time complexity is b to the power L, that is b to the power small l, and the small l here, the small l is the depth limit, and then space complexity is p into l. It is also similar to depth first search, but depth first search it will go up to m, that is the maximum depth. But here it will go up to depth limit l, and it is not, it is also not optimal, and it avoids infinite paths because we are limiting the depth. Then iterative deepening search, it is complete, and time complexity will be b to the power d, and space complexity will be b into d, and also it is optimal if step costs are equal. And it combines the BFS completeness and DFS memory efficient. So both the properties of BFS, that is a better property of BFS. That is, here it is complete, and in the case of here in depth depth of a search, here the space memory efficiency. So these two properties are combined in the case of iterative deepening search technique. Then coming to the bidirectional search, here we have it is complete if both directions use BFS and goal is unique, then it is complete. And here the time complexity will be b to the power d by 2 and space complexity will be b to the power d by 2. And here it is optimal, yes, if both directions, that means forward search and backward search, both uses BFS, then it is optimal. So it searches from both, that means forward search and backward search from start and goal. So here we can, so we have compared all these techniques and uninformed search strategies. So BFS and UCS, that is Uniform Core Search, are complete and optimal. The condition is there, but we can say that these two algorithms are complete and optimal. By general, we can say that. Then DFS and DLS, that is depth first search and depth limit search. Then these two are not complete and not optimal. And IDS, that is iterative deepening search, gives a best trade-off between time and memory. And then next is actually bidirectional search. This is the fastest, but it has constraints, because if there is more than one goal state or goal state should be known clearly, then only we can do the backward search. So here we can say that among uninformed search strategies, IDS provides a balanced solution, that is iterative deepening search. So this provides a balanced solution, while the bidirectional search offers the fastest performance when applicable. So that means if goal state is not and backward actions are also not, then bidirectional search, that will be the best one, because it offers a fast performance. But IDS also provides a balanced solution, because IDS, iterative deepening search, that gives a better, it is fast and also it is memory efficient, because it combines the good property of BFS and DFS. So that combines BFS completeness and also DFS memory efficiency. So this is the comparative study of uninformed search strategies. Thank you. So now we have completed uninformed search strategies. Now next session we will discuss informed search techniques. Thank you.